All of you, please see this slide. Is it visible?
No, sir.
Slide. Is the slide visible? Okay, very good. Okay, today I'm discussing about the class on singularities. For that one, okay, in the previous class we discussed the Lorentz series, series of expansion, and some problems on that. Up to the last class, you see, while we started with the CR equations, Cauchy-Riemann equations to find the analytic function to Lorentz series expansion. We studied the functions which are analytic in a given region. This is we studied. Okay, so where the function is analytic, which region the function is analytic, this is we discussed. But there are several functions we have, so which are not analytic at a certain point of its domain. So such exceptional points where the function is not analytic, such exceptional points are called the singularities of the functions. Okay, these exceptional points, for that one we are discussing the today's topic especially. So such exceptional points are called the singularities of the functions, and type of singular points in that one type of singular point is called a pole, which we have already previously in the class, where the singular point that is we discussed, that is the pole we discussed. So in this study we discuss especially the residues at a pole of functions. This is especially we discuss in this class. Okay. Also, we discuss the without proof, the residue theorem, Cauchy's residue theorem. This is also we discuss. So here, first we discuss the zeros of analytic function. After that, the second portion is the singularity or singular points. Okay, so what type of singular points there exist for the complex functions where the function is not analytic, that point. Okay, especially we discuss in this class. Okay, all of you please write down zeros of analytic function. The definition: a zero of an analytic function analytic function f of z is a value of z, value of z, value of z such that f of z is equal to 0. At that value of z, at that z, if you substitute, f of z is 0. Okay, so particularly if a is called a zero, a zero of an analytic function, a zero of analytic function. What is the function? F of z, analytic function f of z. If this a, if you substitute instead of z, there the function value is 0. So then we call this is the zeros of analytic function. Okay. So here zeros of analytic function after that. So once we find the zeros of analytic function, zeros of what is the order of those zeros? That is for zeros of mth order we discuss. Zeros of mth order. If an analytic function f of z can be in the form f of z we write as z minus a whole to the power of m phi of z. So this function we are writing in terms of z minus a whole to the power of m into phi of z. So where what is this phi of z? Phi of z is analytic function. Phi of z is analytic function. And if you substitute this a in this z, phi of a is not equal. Phi of a is not equal to 0. So phi of z is analytic function, and at this point a, the function value is not equal to 0, and z minus a whole to the power of m. Here, if you substitute z is a, then this is the then z is equal to a is called the mth order of the function f of z. Then 0 of mth order. So then z is equal to a is called 0 of mth order. Of the function f of z. Okay, so this is the mth order, 0 of mth order. Okay, so for example, discuss one problem. For example, suppose f of z is equal to z minus 1 whole to the power of 3. Then z is equal to 1 is 0 of order 3. This is the example. Or another example, f of z as 1 by 1 minus z you take. Then so you see that 1 by 1 minus z means so what value of this f of z is 0, that is z is equal to infinity, is a simple 0, is a simple 0. f of z. Simple 0. Okay. Next, singular points. So a singular point of a function f of z is the point at which the function f of z ceases to be analytic. Ceases to be analytic. That means, so singular point means what? So ceases to be analytic means it is at that point it is automatically stopping means automatically it is at that point the function is not analytic. That is ceases to be analytic means it is not analytic at particular point. Okay. So other than that point the function is analytic. Other than that point the function is analytic. So that is the singular. Okay, so these singular points are around 3 to 4 types we have. In that one, especially we discuss the isolated singularity and essential singularity and removable singularity, singularities at infinity. These are the 4 types we will discuss. First, we discuss the isolated singularity. Isolated singularity. So isolated singularity is a point z is equal to a is called an isolated singularity of an analytic function f of z if f of z is not analytic at that point. Z is equal to a. This is compulsory. And the second one is f of z is analytic in the dilated neighborhood of z is equal to a. F of z is analytic in the, so it is not analytic at that point, and also it is analytic in the dilated neighborhood of this point z is equal to a. f of z is analytic in the z is equal to. So that means what? There is exist a neighborhood of the point z is equal to a, which contains no other singularities. That is the meaning. So f of x, f of z is analytic in the dilated neighborhood of z is equal to a means what? So there exists a neighborhood z is equal to a. For that, there exists a neighborhood of the point at that point z is equal to a, like this one. If suppose this is the way you take, this is the a, so this is the neighborhood. So at this point, uh, the at this point the function is not analytic, but the dilated neighborhood of this point the function is analytic. Okay, and it means which contains no other singularities in this neighborhood. So the dilated neighborhood we are considering means what? So in this neighborhood only, in this neighborhood you cannot get more than one singularities. Okay, only at this point only the function is not analytic, and the dilated neighborhood of this point the function is analytic. So then we call this is the uh, isolated singularity. Isolated singularity. So for example, you see, for example, uh, you see, if we consider function f of z is e to the power of z by z square plus 1, then z is equal to plus or minus ir, two isolated singularities or singular points. Two isolated singular points of f of z. Okay, so plus I or minus I. So e to the power of z by z square plus 1. This is the two isolated singular points. Okay, next. Poles of an analytic function. If z is equal to a, is an isolated singular point singular point, isolated singular point of analytic function f of z, then f of z can be expanded by Lorentz series about z is equal to a. So what is the Lorentz series? Yesterday we discussed the problems on Lorentz series. F of z is equal to sigma n runs from 0 to infinity a n into z minus a whole to the power of n plus sigma n runs from 1 to infinity bn by z minus a whole to the power of n. Okay. So then the series of negative integral powers of z minus a, that means this portion you see sigma n runs from 1 to infinity bn by z minus a whole to the power of n. So this portion is known as the principal part of the Lorentz series expansion. Okay, this is we call as, because this is the same as the first one. Yesterday I discussed. This is the same as the integration of this one is the same as we are getting the this one. Okay, so therefore for this one I am taking this one from minus infinity to plus infinity. In the previous class we discussed. Okay, n is equal to 0 to infinity, and for that one we take the Lorentz series n is equal to minus infinity to infinity. Okay, so here this portion in the Lorentz series, this portion, this sigma n runs from 1 to infinity bn by z minus a whole to the power of n. This portion is called the principal part of the Lorentz series. Okay. Negative powers of z minus a, that is sigma n runs from 1 to infinity bn by z minus a whole to the power of n. This portion is called principal part of principal part of Lorentz series expansion. Lorentz series expansion of f of z. F of z. Okay. So in particular, if we see this part, especially contains some finite number of terms, negative terms we are getting here. So these terms these negative terms, if we consider, is called the pole of order for the function f of z. So that is we write as if the principal part contains some finite number of terms. If suppose we consider these terms are some m, then the singular point z is equal to a is called the pole of order m for this part. Okay, so this part only we consider. So you write down the principal part contains a finite number of terms we say those are m. Then the singular point z is equal to a is called a pole of order m. So these finite terms, these are coming from this sigma n runs from 1 to infinity, principal part of the Lorentz series expansion. Okay, those are called the pole of order m. Okay, so for example, I will show one example, then you will get about this pole of order m. Suppose if we consider f of z is equal to z square by z minus 1 into z plus 1, z plus 2 whole square. This is the function we consider. So then this z is equal to 1, z minus 1. This is z plus 2, we write as z plus 2 whole to the power of at this point z minus 1, you see z is equal to 1, you substitute. This is the simple pole, and z plus 2 whole square, here z is equal to, you substitute minus 2. That means z is equal to minus 2 is the pole of order 2. Okay, z is equal to 1 is a simple pole. It means it is the singularity, isolated singularity only. The pole means. Okay, and z is equal to minus 2 is a pole of order 2. Pole of order 2. So next, essential singularity and removable singularity. These two we have. the principal part of this f of z contains an infinite number of terms, then the point z is equal to a is called the essential singularity. అంటే ఈ ప్రిన్సిపల్ పార్ట్ ఏదైతే ఉన్నదో మనం ఇందాక నుంచి చూసుకుంటున్నాము లారెన్స్ సిరీస్ లో. సో దిస్ సిగ్మా n runs from 1 to infinity bn by z minus a whole to the power of n. So from this one, this contains an infinite number of terms. Okay, this contains the infinite number of terms, and then the point z is equal to a when we take the function value f of z is 0. That means there exists no finite value of n. Okay, but whenever you find the limit z tends to infinity z minus a whole to the power of n f of z, the function what we are considering, that is must be finite. Okay, then we call this z is equal to a is the essential singularity. Okay, first you write down. I will give one example, then you will understand this. If the principal part of f of z contains an infinite number of terms, that is sigma n runs from 1 to infinity. This is the principal part bn by z minus a whole to the power of n, contains an infinite number of terms then the point z is equal to a is called essential singularity. That input 10 minutes is called essential singularity. Essential singularity of f of z. Of f of z. So in this case, what happens? In this case, limit z tends to a, f of z does not exist. Does not exist. This is, you remember it. So for example, we consider the example is, so the function does not exist at that point. For example, you take e to the power of 1 by z. So here z is equal to 0 is the essential singularity for this function, f of z. So f of z is equal to e to the power of 1 by z. So z is equal to 0. So z is equal to 0. The function, you see that how it is, does not exist, the function. So therefore z is equal to 0 is the essential singularity for the function e to the power of 1 by z. Of z. Since the principal part of, you see that the principal part of this function contains an infinite number of terms, whereas at z is equal to 0, the function does not exist. Therefore, this z is equal to 0 is called the essential singularity. Okay. So the last one is a removable singularity. Removable singularity. If the principal part, the principal part of f of z contains no terms, if bn, that is if bn is equal to 0 for every n, then the singularity z is equal to a is removable singularity. So, for example, you see, if suppose we consider the function f of z is equal to sin z by z, then what is f of 0 at 0? We can do f of 0 is not exist. F of z contains no terms, not exist. But you find the limit z tends to 0, sin z by z is 1. So that means if z is equal to 0 is the singularity, z is equal to 0 is the singularity actually, but we can remove that singularity for this function sin z by z. So because limit z tends to 0, sin z by z is equal to 1. that that singularity we are removing. Originally it is a singularity, but we are removing that singularity, then we call it is a removable singularity, we call. Okay, so these are the main important singularities we have. Singularities at infinity also we have. The last one, singularity at infinity. Singularity at infinity. Taking z is equal to 1 by t in f of t. Sorry, f of z kada mana function in f of z. F of z. So then we obtain, you see, we obtain what is f of z, f of 1 by t is equal to capital F of t. Then the nature of the singularity of the singularity at z is equal to infinity is defined to be the same as f of t is equal to 0. F of t is f of t at t is equal to 0. So z is equal to infinity. The nature of the singularity is z is equal to infinity as for this function f of z is the same as t is equal to 0 in f of 1 by t or f of t function. Here you see that z is equal to infinity. Here t is equal to 0 means what? 1 by 0 is infinity. F of t also going towards infinity. F of z is infinity means that is the same as f of t at t is equal to 0. This type of similarities are called the similarities at infinity. Similarities at infinity. So for example, you see that if f of z is equal to z cube and this. So here put z is equal to 1 by t, then what we will get? F of 1 by t is equal to ఏమవుతుందండి ఇక్కడ 1 by t cube అవుతుంది. 1 by t cube అవుతుంది. So అంటే here you see that z is equal to 3 has a pole of order. This is going towards infinity. Pole of order 3, whereas here you see that this is also pole of order 3 at t is equal to 0. So this is the first one. F of z is equal to z cube has a pole of order 3. Okay, are you understand? At z is equal to, because at z is equal to order 3, at z is equal to infinity. Z is equal to infinity కదా, ఇన్ఫినిటీ దగ్గరనే కదా మనకు ఇక్కడ పోల్ ఆఫ్ ఆర్డర్ 3 వచ్చేది. ఓకే, z is equal to infinity. This is the same as f of 1 by t is equal to 1 by t cube has a pole of order 3 at t is equal to 0. At t is equal to 0. This is z is equal to infinity. Okay, the singularity. Here it is t is equal to 0. Is the singularity. అంటే ఇక్కడ z is equal to infinity అని ఎందుకు చెప్తున్నా అంటే z is equal to infinity means what? The function is not defined. At t is equal to 0, the function is not defined. Therefore, the function is not analytic at that point. Z is equal to infinity, the function is not analytic. T is equal to 0, the function is not analytic. So that is called the pole of order 3. This is the pole of order 3. The same. So tomorrow I will discuss the Cauchy's residue theorem, and on that one I will discuss some problems. Okay. So I'm stopping here only the class, today's class. Anything you want to ask, please.